next is a bond parameter. The bond parameters say whenever a covalent bond is formed, then that covalent bond, certain parameters are there which are measured for that particular covalent bond. The parameters like bond enthalpy, bond length, bond angle, bond order, etc. So here we are going to learn some of the parameters which are important, which are necessary to measure for a covalent bond. So let's start with the first parameter, that is bond enthalpy. Bond enthalpy are also known as a bond energy. Bond energy that or bond enthalpy, it is the amount of energy required to break 1 mole of a bond, 1 mole of a particular bond present between the two atoms in a gaseous state. Means, see, as I said in the beginning, that whenever two atoms comes closer to each other, the process is followed by the evolution of energy. Means when the two atoms are getting closer to form a bond, certain amount of energy is released. So if you want to again separate, the breaking of bond means you have wanted to separate these atoms. So if you want to separate this atom, so whatever the amount of energy was released, you have to supply the same amount of energy. If the bond is a strong bond, then during the bond formation, a large amount of energy was released. So that's why the bond becomes a very strong, it becomes a highly stable, because large energy is released, that is energy decreases to a lower value. So the energy decreases to a very higher value. So I can say that the bond form is a very strong bond. So in that case, the energy required to break that bond will be strong. So bond enthalpy is nothing but the energy required to break a particular bond present between the two atoms in a molecule in a gaseous state. For example, suppose I want to measure the bond enthalpy for the hydrogen molecule. So hydrogen molecule, that is a bond is formed between the two hydrogen atom. And if I wanted to break this bond, suppose, then for breaking of this bond, after breaking this bond, hydrogen will get separated. I will get two hydrogen atom. But at the same time, a very large amount of energy is required to break this bond, and it was approximately 436 kilojoule per mole. If you'll observe the unit is kilojoule per mole. Kilojoule is the energy unit. Per mole means what? This energy is not the meaning of this per mole unit is that this energy is not required for breaking a single bond, but it is required to break such a hydrogen bond. 1 mole of hydrogen bond means this much the energy is required for breaking 1 mole of this bond. And 1 mole of this bond will present in a 1 mole of H2. So 1 mole of H2, in 1 mole of H2 there is a 6.022 into 10 raised to 23 such bonds which are broken by supplying so much amount of energy. So this value is always for 1 mole of a bond. And again the bond enthalpy is always measured when the substance in a gaseous state. Then second after hydrogen, I can write for chlorine. The energy required for breaking this chlorine bond, or after breaking I will get ClCl, and the energy when we measure it was approximately 242 kilojoules per mole. Similarly, for oxygen molecule, the energy measured, oxygen double bond, so slightly more energy will be needed because double bonds are generally stronger than single bonds. So oxygen double bond, so it is energy is here 494 kilojoule per mole. For nitrogen molecule N triple bond N, triple bond, the energy needed is 946 kilojoule per mole. Now if with the help of bond energy, I can say that in air which is a mixture of oxygen and nitrogen gas, which contains approximately 78% nitrogen and only 21% oxygen. But whenever we write the reaction of an element with air, whenever I use the word the reaction with air, the first we think only about the oxygen. We never think about the nitrogen, the reactivity with the nitrogen. The reason, because the oxygen is much more reactive than the nitrogen. See, for a reaction, the bond between the two oxygen atom or the bond between the two nitrogen atoms should break. And you can see from the value that for breaking a bond between the oxygen atom is only so much amount of energy is needed. While in case of nitrogen, the energy required is approximately double, that is 946 kilojoule per mole. And since here the energy required for breaking a bond, that is to make the nitrogen atoms reactive, is very high, and that's why we say that the nitrogen is the least reactive gas because of its high bond enthalpy. Okay, similarly I can say that the number of bond, the energy, now the bond enthalpy depends upon the certain factors. The factors are, I can say, like number 1. Okay, before that factor, let's see some more example. Suppose I wanted to break a bond between these are the homoatomic molecules. Let I'm considering HCl molecule. HCl, the bond energy required for this is approximately 431 kilojoule per mole. Means if so much amount of energy is supplied, this bond will break and hydrogen and Cl will separate it. And once hydrogen and Cl will separate it, that means they become highly unstable and they will react. Similarly, suppose I wanted to write the bond enthalpy for H2O. For H2O molecule, I know that there are the two types of bond. There are two bonds, that is between this HO and between this HNO. But you can see that both the bonds are same. This bond will be considered as OH bond. This bond will also considered as a OH bond. When I measure this energy for this, after breaking of bond, this 2 hydrogen will separate it and you will get a 1 oxygen, and we measure the bond enthalpy. It was 929 kilojoules per mole. Means this much amount of energy was required. Now in the case of this, when we measure the bond enthalpy for a single bonds, that is first I break this bond. So the energy required for breaking this bond, means after this we will get H, 1H is separated plus OH is left. Here when energy is measured, it was 502 kilojoule per mole. Similarly, when second OH bond was broken, that is this one, we will get O plus H. That is delta H is equal to 427 kilojoule per mole. Now here the shocking thing is that we are breaking the same bond in both the cases. That is here also the OH bond, here also we are breaking the OH bond. But still the energy required for them is different. That is in the first case of 502 and second case of 427. The difference in the energy is, I can say that it's because of the change in environment, the chemical environment of a molecule. For example, initially it was a neutral molecule, that is H2O, but after breaking OH, OH becomes a less stable, and being a less stable, here the energy required is less. In certain cases the energy required in the second case is more, in certain cases it is less. For a different molecules, the energy changes differently. It's not like always first is more and then second is less. Okay, after that, the bond enthalpy. So here if someone is asking, the question comes like, what is the bond enthalpy for OH bond? Delta H of OH bond in water. Now delta H of OH bond in water means I have to somewhere write the energy required to break OH bond in water. But the main question in my mind is that here for breaking OH bond we have two different values, that is 502 and 427. So which value should be written as an answer here? So in that case, here we consider the average energy of both, that is 502, 427, and we called it as the average bond enthalpy for OH bond. So if in a molecule the same same type of two or more bonds are broken with a different energy, then in that case we always write it's a average bond enthalpy. So average bond enthalpy for this will be 502 plus 427 upon 2. That means here I can write it as a 929 upon 2. This is 2 4s are 8, 2 6s are 12, 2 4s are and 2 5s are, that is kilojoule per mole. So this is the average bond enthalpy for OH bond in water. Now there are the certain factors which affect the bond enthalpy. Now let's see those factors. The factor number 1, size of atom. Here for the size of atom, I can say that smaller the size of an atom, smaller will be the bond, smaller the bond, more stronger it will be, so more energy will be needed to break it. For example, suppose this is an atom A and atom B, the bond is formed between A and B. Let A is also smaller and B is also smaller. So this is the bond with this A and B, this is the bond length. Bond length, that is the distance between the nucleus. So bond is smaller one, and if the small bonds are always stronger one, and if the bond is strong, then simply I can say the energy required to break that bond will be much high. At the same time, suppose if I'm considering two atoms like C and D, bonds, the atoms are comparatively bigger than A and B, so the bond length will be, so here the bond will be the larger, and since the bond length is a large, so the bond is going to be weaker one, and if the bond is a weak, that is a less energy required to break the bond. Okay, so this depends on the size of an atom, so I can say that bond energy is inversely proportional to the size of atom. Smaller the size, smaller will be the bond, and higher the energy will require to break it. Okay, after the size of atom, the second thing which affect the bond energy, the next is the multiplicity of the bond. Multiplicity of the bond. As the number of bond between the two atoms increases, the bond enthalpy or the bond energy also goes on increasing. More the number of bonds, more will be the attraction and more will be the energy required to break that bond. For example, suppose if there is a carbon-carbon single bond, then energy required for breaking this carbon-carbon single bond is 433 kilojoules per mole. That is, in case of alkene, if you wanted to break a bond between the two carbon atoms, then this much amount of energy is required. Then similarly, carbon-carbon double bond, the energy required is 619 kilojoules per mole. And third, if there is a carbon-carbon triple bond, then energy needed is approximately 836 kilojoule per mole. So this is about the multiplicity of the bond. I can say that the atoms are same, but if the atoms are same and if the number of bonds goes on changing between the two atoms, then it is called, then the bond energy goes on increasing. And the number of bond formed between the two atoms is called as a bond order. So I can say that as the bond order increases, bond order 1, 2, 3, as the bond order increases, the energy required to break the bond increases. The reason simple, single bond, in double bond, the attraction will be more, so more energy is required. In triple bond, the attraction will be still more, so more energy is required, that is 836 kilojoule per mole. So I can say that here the bond energy is directly proportional to the bond order or multiplicity of the bond, that is a bond order. Third one, bond length. The dependency of the bond energy on the bond length, I explained here only, that if the atoms are smaller, the bond is going to be strong and hence the more energy will be required. If the atoms are bigger, the bond length will be high, so that bond will be weaker and the less energy will be needed. That is, smaller the bond, stronger it will be, and hence the energy required will be more. So I can say for the bond, in terms of bond length, that bond energy is inversely proportional to bond length. More higher the bond, strong bonds are always smaller in size and the energy will be large. Okay, so this was about the first parameter, that is a bond enthalpy. Now let's see the second parameter, that is bond length. Okay, second parameter, bond length. What is bond length? And simply, as I said, it is a distance between the nucleus of the two combined atom. Bond length, I can say, for example, suppose this is an atom A and B, I just wanted to measure the distance between A and B, the bond length of A and B. This is atom A and this is atom B, so bond length means the distance between the combined atom. It's a bond length. This, since the bond is a covalent bond, so they slightly overlap with each other, which is not properly shown in the diagram, but they are overlapping. Okay, but the thing is that bond length, it's nothing but the distance between these two combining atoms. This distance is called as bond length. So it's a distance between the nucleus of the two combining atom. As I said, bond length decide the strength of a bond. Weak bonds are always stronger, the smaller bonds are always stronger, while the weak bonds are always, small bonds are always stronger, while the large bonds are always weaker. Okay, now with the help of bond length, one more thing. The bond length is generally measured in terms of picometer. The picometer, which I can say is equal to nothing but the 10⁻⁻12 meter. The bond is calculated by using that X-ray spectroscopy or X-ray spectroscopy. Now, bond length, with the help of bond length, we can calculate the radius of an atom. But for this, the condition is that the two atoms which are combining, they should have, both the atoms should be the same. Like for example, suppose I wanted to know the bond radius, the radius of a chlorine atom. Then here for the chlorine atom, we consider this the first chlorine. And this is the second chlorine atom. As I said, they overlap. Just find out the distance between their nucleus, that is the bond length, with the help of that X-ray spectroscopy. So let I find this radius. I come to know that this radius is 198 picometer. So if you want to know the radius, then radius is equal to half of bond length, that is 198 upon 2, that is equal to 99 picometer. And now this radius is known as a covalent radius. What? It is called covalent radius. The covalent radius, because this radius has been calculated with the help of this covalent bond. And one more thing, if you can observe that if you're calculating is half, then half will be the distance between this, or the distance between this and this. That means here I can say that the covalent radius is not the actual radius, but somewhere it is slightly smaller than the actual radius of an atom. So covalent radius are always smaller than the actual radius of an atom. Okay. Now here if you want to, as I said, this is the bond length. So this is, I'm representing bond length by R, which is nothing but the radius of A plus the radius of B, we generally say. Okay. After the bond length, bond length, I can say with the relation, is directly inversely proportional to the bond energy, as I said, because if the bond length is inversely proportional to the strength of bond, that is smaller the bond, smaller the bond, stronger the bond will, the smaller bonds are always stronger one, and if the bond is big, then the strength will be weak, that is a weaker bond will be weak, and so that bond energy will be less. So bond length is inversely proportional to strength of bond, or I can say bond energy. Second thing, as the bond order increases, the attraction increases, and hence I can say again that bond length goes on decreasing. So ultimately I can say bond length is inversely proportional to the other parameters. Okay. After that, so the third bond parameter is bond angle. Covalent bonds are directional bond, and being a directional bond, they always orient, or during the overlapping, they orient in a proper direction of the orbitals which are overlapping. Means the covalent bonds are always formed in a particular direction, and if it is forming in a particular direction, and if there is a two or more than two bonds present in a molecule, then we can calculate the distance or the angle between those two atoms and those two bonds, and that angle is going to be the same for the same type of molecules. For example, suppose if I have H2O molecule containing the two bonds, and we have the value, that is in case of H2O, that is this, it is having a V shape, and this bond angle is measured as 104 degree 35 minutes. Similarly, we have a bond angle for the ammonia molecule also, that is NH3. This is ammonia. Here we have a lone pair electron, and then these three hydrogen we have. And when we measure here the bond angle means either this angle or this angle, then I come to know that this bond angle is 107 degree 18 minutes. That is, this is called as HOH bond angle, and this is called HNH bond angle. This angle is also same, that is 107 degree 18 minutes. Similarly, we can write the bond angle for the methane also. Methane, that is CH4, there's 4 hydrogen which are tetrahedrally attached to the carbon. So here all the bond angles, we have 4 bond angles. All bond angles are same, that is 109 degree 28 minutes. So here, since the covalent bonds are always formed in a particular direction in a space, and that's why we can measure bond angle. Then the fourth parameter which we have is bond order. Bond order. As I said, bond order is nothing but the number of bond formed between the two atoms. The number of bond formed between the two atoms is called as a bond order. For example, here the bond order is for in alkane the bond order between the two carbon atom is 1. Here the bond order is 2. In this case the bond order is 3. If someone is asking that what is a bond order for H2 molecule, that means he wanted to know the number of bond formed between the two hydrogen atom in a H2 molecule. So between the two hydrogen atom the number of bond form is 1. In O2 molecule the number of bond form is 2, and in case of nitrogen the bond form is 3. So the bond order, that is a number of bond formed between the two atoms, and as the bond order increases, I will say that strength of a bond increases. The strength of a bond increases, which says that the bond energy will also increase. It means I can say that the bond energy and the bond order is directly proportional to each other. Okay, here we have this covalent radius. There is a one more term that is called as a van der Waals radius. Now what is van der Waals radius? Suppose this is the first chlorine molecule and we have another chlorine molecule also. This chlorine molecule. Now we have two chlorine molecules, suppose. Then chlorine is in a gaseous state, and being a gaseous state, and here it has been observed that the attraction which is present between the two chlorine molecule is a van der Waals force of attraction, and or I can say London force or dispersion force, because the chlorine molecule is a non-polar molecule. So the attraction present between the two non-polar molecule is considered as a London force or dispersion force. So here the attraction present between the two molecule is weak force of attraction. Okay, now what happens in the case of van der Waals force? Suppose this is the first Cl2, second Cl2. They comes closer, again they moves away from each other. They comes closer because the nucleus attracts the electron of this and this nucleus attracts the electron of this. But once they reaches closer and closer, attraction increases but simultaneously repulsion also increases. And a time comes when the repulsion becomes more than attraction. Repulsion between the nucleus and electron of this and electron of this. And so that they, instead of once they reaches to a certain distance, again they moves away from each other. That means I can say that two chlorine molecule does not touches to each other. So in that case, here we calculate the van der Waals radius. Okay, so here we calculate this attraction. This attraction is called as a van der Waals force. Suppose these two molecules are at the closest distance. Now bringing them still even more closer is not possible. So in that case, the attraction present between them is called as a van der Waals force. We just find out its half. Again, this attraction is nothing but between the nucleus, I can say. This length is between the nucleus. Here for the chlorine molecule, this length is calculated as 360 picometer. How much? 360. So if I'm making its half, then it will be 180 picometer. And this value is called as van der Waals radius, which is equal to 180 picometer, and you can see that which is much higher than the actual radius of the atom. Actual radius is slightly greater than covalent, and which is very much smaller than van der Waals radius, because the van der Waals radius is much higher than the actual radius of an atom, and which is calculated with the help of van der Waals force of attraction present between the two molecules. So these are the four bond parameters which we are having in a syllabus. That is the bond enthalpy, energy required to break a particular bond present in a 1 mole of a substance in a gaseous state. Bond length, the distance between the nucleus of the two combining atom. Bond angle, the angle formed between the two bonds. And the bond order, that is the number of bond formed between the two atoms. Here we can say that the bond length, bond energy, and bond enthalpy, bond order, and the strength of bond, they are directly proportional to each other, and all three are inversely proportional with the bond length. Bond length inversely proportional to bond enthalpy, inversely proportional to the bond energy, and inversely proportional to bond enthalpy, inversely proportional to bond order, as well as to the strength of a bond. So this is about the bond parameter.